when we talk about conventional radiography, or also known as analog radiology, this is what most of us grew up with film-based system, where we would look at, we would take an X-ray using film. And when they first started with X-rays, they used glass plates. You've all heard the term flat plate. Let's take a flat plate. Flat plate was a term that came from glass plates that were painted with emulsion. And those were used up until World War I. It wasn't very convenient to carry glass plates out on the battlefield, so they came up with a based film and got away from the glass plates. And we've been using polyester-based film for a number of years now, although that has been replaced now with digital radiography. How many of you are still using a film-based system that you know of in your radiology departments? They're still using films and view boxes? They are? No? Oh, fluoro, okay. So, so most of us grew up with film and the imaging system from film and CR. If you talk about a film screen system versus a CR system, computed radiography, versus digital, CR is a form of digital, but it still uses a cassette. Okay, so a cassette or a plate that we use to expose X-rays with, whereas pure digital, direct and indirect digital, uses no cassette but exposes an imaging plate that's built into the machine itself, kind of like your II tube that's built in with the X-ray, and the II tube is the image receptor, okay, which is a form of digital. So analog radiology involves film. And this is what I was trained on with film and have had to learn digital since then. But with film, we use regular radiographic film, which has a base to it, which is made out of polyester, and then painted onto that base is a silver bromide emulsion that is light sensitive. Okay. So the film is placed inside of something called an intensifying screen. Have any of you ever worked with cardboard holders? Back in the 70s, they had cardboard. I trained on cardboard holders. And cardboard holders is when we take the X-ray film, place it into a light, tight envelope that was made out of cardboard, and directly expose the X-ray film to radiation. We went from that to image intensifying screens that were made out of calcium tungstate, was the phosphor. And when you put the film inside of a cassette that had image intensifying screens in it, the X-ray would cause the phosphor to give off light. The light would expose the film as opposed to the X-ray and produce the image. But because light diverges, the resolution or the sharpness of the image wasn't as great as the direct exposure film. Now there is one area that they're still using direct exposure film. Some physicians are still using direct exposure film. Does anybody know where that is? You probably all had this done to you at one time or another.
Scoliosis.
No. Dental film. The dental film, the little films that they place in your mouth, are films inside of plastic, and they're direct exposure films. They take about 200 mass, remember MAS, not MASS. They take 200 mass of exposure for each film, and a full mass series is about 20 films. So they use the low kVp, 50 to 55 kVp, 200 mass, but you get excellent detail or excellent resolution because the X-ray itself is exposing the film, and there's no divergence of the ray like you get with a cassette. Now, we used to use, for a hand X-ray, just as an example, 50 kVp at 100 mass for a cardboard exposure. Once we got image intensifying screens, we'd take the same hand, we used 50 mass at 50 kVp at 5 mass. That was with the calcium tungstate screens. And then we went to rare earth screens that were made out of gadolinium, and we used 50 kVp at 1.5 mass. So what's happening with each one of these? The speed of the system is getting faster and faster and faster. As a result, you also lose detail. So the price you pay for a faster system is you get less detail. But it was enough detail, given the dose that you would get with the direct exposure, that it was acceptable. And when you're getting a fraction, 1.5 mass as opposed to 100 mass for a hand X-ray, it was worth the trade-off. And we see the same thing happening with digital radiography. It's a faster system, but the detail is not as great. Okay. It turns out when you read films, spatial resolution isn't nearly as important as contrast resolution, how contrasty it is. The faster the system, the higher the contrast. Okay? It's more black and white. Those two tend to go together. Okay, so we put a film inside of these screens. We make an exposure. So the film's actually located. This is the fluorescent screen here. Okay, and this is the film base right here, and another screen back here. So it's actually 95% of the exposure on the film is from the fluorescent light coming off of the screen. Screens are much more sensitive to radiation than film is, as you can see from going from 100 mass to 1.5 mass. More sensitive, but you lose a little bit of detail. Now what's happening inside the film is made out of silver bromide, another term is silver halide, and when we expose the film to light or X-ray, it ionizes the silver bromide crystal. So the silver breaks apart from the bromide, silver becomes positively charged, bromide becomes negatively charged, and all of the silver will migrate to what's called the sensitivity spec, which is made out of sulfur. When you get about 10 or 12 silver atoms or silver ions on a sensitivity spec, that spec becomes developable. So that spec, when I run it through a processor, will be black. So the silver is converted to black metallic silver, which creates density on the film. So the areas that are exposed will be black, and the areas that are unexposed, we wash off all the unexposed silver from the film, those areas will be white, giving us an image. If you have more silver together, it will be darker. Less silver together, it will be grayer, or no silver on the film, it will be clear, giving us our scale of contrast. So we take films and we run them through processors. I feel sorry for the guys that used to work for Kodak. Everybody used to have a Kodak processor, and most of the processor, the guy that works on our processor at the college is now working at Trader Joe's. I mean, this is an industry that basically it's gone. It's not coming back. You know, the processors are gone, and everybody's gone to digital now. And so it was a huge industry at one time, but no longer. So we run our films through processors. The longer the film's in the processor, usually the better the contrast will be. If we're doing mammography and still using films, we have 5-minute processors. By keeping the film in the developer long, it brings out the darker areas more and the clearer areas more and gives the film more contrast. Most departments use 90-second processors for normal X-ray. Now, on the film, we have something called an H&D curve. An H&D curve tells us the characteristic of that particular film and the shades of gray that will be visible to us on the X-ray. So when we look at this H&D curve, what it's showing us is both the contrast of the film, the speed of the film, the latitude, how much error I'll have with the film, and the spectral matching of the film. So there's a lot of information on this H&D curve, but the thing I want you to know about this H&D curve is that there's only one area that we can actually see well on the film, and this is called the useful range of density. So this is the toe of the curve. Below this area, the film is too light. When we get up to this area, the film is too dark. We like all of our films to be in this useful range between 0.25 and 2.5 density range. And it's a logarithmic scale. Now down here we have log relative exposure. This is a log of 2, and basically with each one of these plots they're doubling the exposure. So when we look at the useful range and how many exposures we can make within the useful range, we call that the latitude of the film. How much room for error do we have? Now with cardboard cassettes, when I said that the film is not very sensitive to radiation, you could use 500 mass or 100 mass and basically get the same scale of contrast on your film, as long as you have the right KVP. With a rare earth system, if I use 1.5 mass or 2.5 mass, that's almost the difference between too light or too dark. 5 mass, you're way out of the ballpark. Less than 1 mass, you're way out of the ballpark. So the faster the system, the narrower your latitude is, your range of exposure is. But when we look at this scale, this has 4 decades. Oh, sorry. Each one of these this is logarithmic, so this is 10, 100, 1,000, and 10,000. So the range that we're looking at is about 100 to 1,000 shades of gray. Now here's the bad part. So the film's recording 100 to 1,000 shades of gray. How many can we see? Only about 30. The scale of gray that we're actually able to visualize is only about 30 shades of gray on a particular film. So the H&D curve is going to be between 0.25 and 3.0. Now this is going to become important when we talk about digital later on. Okay, so what about computed radiography? Well, this is the new craze. This is what everybody's going to, and it's here to stay. With computed radiography, CR, I'm not talking about DR, which is digital radiography. Computed radiography also has a cassette with it. Okay, it has a holder for it. But instead of film inside of the cassette, we have a phosphor plate. The phosphor plate is made out of polyester. It has the phosphor painted on the top of it. Now, this phosphor plate is not sensitive to light like X-ray film is. X-ray film, you had to have a dark room, right? These are run with what we call daylight readers. So you don't have to have a dark room. You don't have to have any chemicals. The plate can be used over and over again. You can pull it out of the cassette and expose it, and there's no effect to it. It's not sensitive to the light spectrum. It's only sensitive to the X-ray spectrum. On this plate, we have these phosphors that are called photostimulable phosphors. Photostimulable. So they can be stimulated by laser light. So it's a red light that stimulates these phosphors, not white light. So on these plates, they're made out of various elements, but barium fluorohydrate, which has fluorohalide has bromide in it. These are activated by the X-ray. So when the X-ray strikes this phosphor, what do phosphors do when they're struck by X-ray? Typically, they give off light, right? 50% of the light is given off initially with the exposure. The other 50% of the light, or the excitement, the electrons are excited to a higher state. It's called a metastatic state. So they're excited, kind of like when we talked about Compton interaction. Remember, the X-ray caused the atoms to get excited. They weren't ionized, but the electrons are excited to a higher state, and they stay in this state until you unexcite them, until you bring them back into a stable level again. How do we do that? By using a laser light. We can expose them or stimulate them with a laser light, which will put them back down into their orbit, and when they come back down into their orbit, they'll give off light again. Okay? That light that's contained, or the position of these electrons on the plate, is called the latent image. Just like we had a latent image on a film. If I take a chest X-ray of somebody with an X-ray film, after I take the X-ray and I'm carrying it to the darkroom, there's a latent image on that film of all the ionized silver, right? And I develop that, wash off the unexposed silver and develop the ionized silver. Same's true with this plate. We expose it to radiation. The phosphors on the plate get excited. Those that are exposed to X-ray are in this excited state. And then I'm going to run the plate through a reader, which will cause the phosphors to go back into their stable state, giving off light, which is the density on the film. And that light is converted to an electrical signal, or digitized. So the analog image is digitized into an electrical image that's carried to a computer and then read out on a screen in pixels. Now, the resolution of a digital image is always going to be dependent on the number of pixels that you have. When you're talking about film, which has silver in it, silver molecules are very tiny, the amount of data that you can put on a film is almost immeasurable. But the amount of data you can put on a monitor is directly proportional to what? Pixels. The number of pixels. Each one of those pixels will produce a density. And that density you'll see as being dark or light. So the resolution is going to be dependent upon the number of pixels and the size of the pixels that you have in your image. So is the resolution of digital imaging as good as film? No, it's not. It's poorer than film. Typically, the resolution of digital imaging is about 5 line pairs per millimeter. A line pair is a little grid that we use to measure resolution, and it's got all of these strips of lead separated from one another. And the more we can count per millimeter, the higher the resolution. For film, we're talking of anywhere from 10 to 20 line pairs per millimeter. Digital, about 5 line pairs per millimeter. So you can see it's about maybe a fourth of the spatial resolution that film is. So why all the big hoopla about digital radiography? Because the post-processing, the contrast resolution is way better than film. I said on a film you can see 30 shades of gray. On digital you can see 10,000 shades of gray. Much, much higher contrast resolution. Turns out contrast resolution is way more important as far as diagnosis goes than spatial resolution. CT. How many of you have ever looked at a CT image? The beginning CT images, even today. What do you notice when you look at a CT image? Are they nice and sharp and clear? They're pretty modelly, aren't they? They're pretty blotchy looking, but they have excellent contrast resolution. You can separate the kidney from the liver. You can separate the spleen from the stomach. You can't do that on an X-ray normally because the contrast of the two parts are too similar. Thank you. They're too similar. But on a CT, you can separate out contrast resolution. So contrast resolution turns out to be much more important than spatial resolution. And therefore, digital radiography has really taken off. It took a number of years to prove this, especially with mammography. How many of you read about the DMIS trials? Diagnostic mammography imaging study trial that they did on 50,000 women. It was done for about 10 years because a lot of radiologists didn't want to buy digital mammogram machines. They cost 4 to 5 times what a normal X-ray machine cost, a regular mammogram machine. But after they did a study long enough, they found that digital mammography was better in diagnosing breast cancer in women that had dense breasts. Now, a lot of women have dense breasts because of these shades, post-processing enhancement. Even though the resolution wasn't as great, when you get the image on the monitor and you can magnify it and you can take different shades of gray and bring those out, they could find densities in dense breasts that you couldn't find in film. On a film, basically what you see is what you get. Whatever you put on the view box, that's all you can do with it. With digital, you can enhance it. You can enlarge it. You can take each scale and the 1s and the 2s and 3s and the 4s, and you can get those 30 shades of gray out of each one of those scales. Okay, so we have this phosphor plate, photostimulable phosphor. We expose it to X-ray. It gives off light immediately during the exposure, but 50% of the light is captured at this excited metastatic state. Then we take that phosphor and we're going to process it. The latent image is on the plate itself. It's not sensitive to normal light. We put it in a daylight processor. Now, the plates have to be processed within 8 hours because what will happen is eventually that excited state will relax and the image will fade. So we try to run the plates as quickly as possible after the exposure. We use this reader. This is computed radiography. Remember, computed radiography has a cassette. So it's very easy to use these cassettes in place of film cassettes. It was an easy transition for most radiology departments. They didn't have to go out and buy new equipment. They could take their old film screen cassettes and replace them with these computed radiography cassettes. The only thing they had to get rid of was the darkroom and buy these readers instead. These readers cost about $70,000, anywhere from $50,000 to $100,000, depending on how fast they are, how many images they'll read. Okay. So inside of the reader, there is it's driven, mechanically driven. It pulls the plate out of the cassette, and then there's a laser light that's very, very small, very fine, and the laser light is going to go back and forth on the plate and stimulate the plate to give off light. The light that's still held is the latent image inside of the plate. Okay? Once that happens, once the light is given off, there is another component here, okay, and this captures the light. Okay, this is a diode, and it converts the light to electrons. So now what we're basically doing is converting the analog to a computed image. So this diode will capture the light coming off of the plate at the same time, and there has to be a filter so that these two lights won't interfere. This is blue light coming off of the plate and red light that we're scanning it with. Okay? So that light is captured, it's taken to the computer, and then it's read on the computer. And it usually takes about 10 seconds, 10 to 15 seconds once you put the plate in and it's read for the image to come up onto the computer. Okay? And then there's an analog on the computer that it's going to try to capture the image and match it with the analog of the part. So that's computed radiography. We also have something called digital radiography where there is no cassette. In place of the cassette, you have a receptor that is built into the machine. A lot of times we call this our bucky, or where we put the film. But there's no film involved. But you have a plate here that can be erased automatically and a new image formed each time. So this plate is connected directly to the computer, and it has a light sensitive, this is called a charged couple device for digital radiography. And the X-ray exposes cesium iodide, which is the phosphor. It produces light. Right below that, we have selenium, and the selenium absorbs the light and converts it to electrons, and then the electrons are transferred to the computer. Okay, so it's basically the same process without the film. The nice thing about these charge-coupled devices is they're very light sensitive, meaning it doesn't take much light to stimulate them. So if they're very light sensitive, you can use lower levels of radiation, thereby saving patient dose. Okay? So we've got a silicone-based semiconductor that's located underneath. That converts the light to electrons, and then the electrons are transferred to the computer, which produces the image for you. Okay, it also has a large dynamic range. So DR, when we're forming the image, this is your photostimulable phosphor made out of cesium iodide, kind of like in your image intensifying tubes. That's your input phosphor. It's made out of cesium iodide. And then below that, we have the silicone here, selenium. Well, let me see, let me go back one. Silicone, yeah. There's also selenium, which is a direct DR. So it's converted to light, and then it's captured, it's converted to electrons here, and then goes to the computer as an electrical signal. So basically digitized. Now this is the beauty of digital radiography. CR is a form of digital radiography, and then direct exposure like I just showed you. But here's our old H&D curve, and this is with a 400 speed system. Okay. Now what do we say about this area of the curve? What's wrong with that? The toe of the curve? It's too light. Really, the image, the film is not sensitive in that range, therefore those light areas are undiagnostic. What about this area of the film? What's wrong with this area? Too dark. The only portion that we can use is this straight line portion known as the useful portion of the curve. Now look at digital. This is exposure in milliroentgen here. So this is 1/100th of a milliroentgen. This is 1/10th of a milliroentgen, 1 milliroentgen. So in these areas, you're just getting into the useful range on the H&D curve here, but look at this. We're producing all of this useful range of the H&D curve is produced at very low light levels on DR. Okay, so digital radiography is much more sensitive at capturing the light that's created from the X-ray, thereby reducing the dose. Okay, again, we don't have the spatial resolution, but look at our contrast resolution in comparison. 10,000 shades of gray, even though we can only see 30 of them, post-processing, we can take any area, this area, this area, this area, this area, and enhance it back to those 30 shades of gray that we're able to see. So basically, when you talk about latitude, what's my margin for error with a DR system? Huge. I can use very little exposure, or I can way overexpose the patient and still come out with a great image. Okay? Once in a while, you'll get an image that's underexposed. We call it a high S number if you're using a Fuji system. You get an image that's underexposed. But most of the time, we have a latitude of 300% of underexposure and 300% overexposure. Now, the bad thing about that is people, when they're not sure, what do you think they tend to do? Overexpose. Because an overexposed image, nobody's ever going to kick that back to you. The information is all there. There's tons of information on that image that they can take. An underexposed image is going to be modelly to the radiologist, and they may kick that back to you. So the fear is that people that don't know how to use digital are going to overexpose their patients because they're going to get a good image regardless. Okay, so they err on the side of overexposure. But this whole system does respond more readily to lower doses of radiation, thereby reducing dose. So what's the advantage? Well, first of all, you can get rid of your darkroom, right? We got rid of our darkroom techs, we got rid of our file rooms, we don't have to store the images anymore, they're stored in a computer. The biggest hurdle that digital radiography had initially was how to store it. We didn't have computers big enough, we call it a PAC system now. We didn't have computers big enough to store these images because each image has a JPEG image, right, has a lot of information in it, a lot of data. So that was the big hurdle, but they came out with jukeboxes and all sorts of things to store the images, so they've gotten over that. So faster time, because we don't have to process the films anymore, takes up less space, less people, and lower dose. Wow, that was quick. Okay, that was a lot of information. If we finish up a little bit early today, I'll have a chance to go over these tests with you, so don't worry about time. We'll use all the time. But are there any questions? Yes?
Yeah. How long, what is the lifetime of these coupled digital, the phosphors in these digital radiography and these coupled systems? In other words, the light hits it and then it sends the message and then it restores back to its, whatever its baseline.
How long does that process take?
Yeah. Well, no. How long do they last? I mean, after you.
The plates so far, I mean, we've had digital radiography in Santa Barbara since about 2002. And the main problem with the plates is when they're pulled out of the reader, there's a mechanical device that actually grabs the plate and pulls it out. They tend to get frayed along the edges there. But other than that, the phosphors don't tend to wear out like the old calcium tungstate phosphors did. Yeah, or like the cesium iodide phosphors did. So far, so good.